Hello, this is Mr. Gilmore with the 1.4 Angle Relationships and Categories lesson. Today we're going to encounter quite a bit of angle relationships in terms of their definitions, which means if I move too fast for you, I would suggest that you pause the video so that you can capture the definition in your notes. This is going to be helpful not only for you in the future here with this lesson, but for future lessons because we are going to encounter a number of these angle relationships throughout the course of geometry. So let's go ahead and jump into some of the very first angle relationships and what we call these. We're going to give them a name, we're going to give them definitions, and we'll also see a diagram that comes along with them. So the first one that we're going to encounter quite often is what we call adjacent angles. We simply just say two angles are adjacent when they have a side in common, but their interiors do not overlap. Essentially think of, right, the interior is the mouth of the angle. We do not want these two mouths of the angles to overlap. We want the adjacent angles to share a common ray or common side. So in our example down here below, we have actually a pair of adjacent angles. We have this angle here, BAC, and this angle here, CAD. Those would be considered adjacent. Why? Well, that they share a common ray. They share a common side. AC is their common side. And also, notice that where I marked the two angles, their interiors do not overlap. If I were to pick two other angles, let's say I picked two different angles other than these two in this diagram. Let's say I picked, let's say I picked this angle here, BAC, but then I picked the entire angle, BAD. Are those adjacent? Well, you may argue, hey, don't they share a common side? Yeah, they do. They share this ray together, don't they? But their interiors do overlap, which means can't call those adjacent. We're going to encounter in the future here some information about adjacent angles and how they will work with some of our very first theorems. We'll see some theorems in the next chapter. Let's talk about vertical angles. Vertical angles, if you may Google this and find different definitions. The vertical angles have many types of definitions. We're going to stick with this one. I like this definition. It says two angles are vertical when their sides, remember sides are rays, form two lines. So for example, if we look at this diagram down below, it looks like we see two lines, and we should, because that's what vertical angles are. They form two lines. A pair of vertical angles in this diagram would be this angle here, angle ABC, and the pair that goes with it, or the angle that goes with it, is angle DBE. So these two angles here are what we call vertical, and they're vertical because their sides, again, form two lines. So really the only thing that these two angles have in common is the vertex. That's what they share. That's the only thing that they share. Here's what's interesting then about the vertical angles. Whenever you create a pair of vertical angles, you technically create a second pair of vertical angles because angle ABD and angle EBC, those two angles are another pair of vertical. So whenever we see essentially two lines crossing, we know there exist pairs of vertical angles there. Let's take a look at another relationship. Linear pairs. Notice that our diagram didn't change. Yeah, the diagram didn't need to change. We actually have examples of linear pairs in this diagram. Let's take a look at this definition first. Linear pairs really have two things involved with them. You're going to see this word "and" here in the middle of the definition because there's two things that are important about linear pairs. So two angles form a linear pair when they are, first thing, adjacent. Meaning, remember, adjacent, they have a common ray, they have a common side, and their interiors don't overlap. So we can unpack that word adjacent there. That's the first thing linear pairs are. They have to be adjacent. And second, their non-common sides form a line. Non-common, meaning that if they're adjacent, they have a ray in common, but there are two other sides, two other rays that are not common. They are not shared by the two angles, which means those two rays form a line. Let's take a look at our diagram here below. I can quickly see several pairs of linear pairs here. Let's take a look at first angle ABD. Oops, let's try that again. Let's look at angle ABD. Oh my goodness. There we go. Angle ABD actually forms a linear pair with angle DBE. Why? Well, it meets both of the criteria that we have in the definition. The first one is that they're adjacent. Yeah, they have a common ray. Yeah, there's our common side. BD is the common side. and their non-common sides form a line. Look at line AE here. This is the line AE. That right there is a prime example of a linear pair. ABD and DBE form a linear pair. There are three others in this diagram. I'm not going to show you all three, but if you take a look, we can find another pair. Let's go back to our first angle, angle ABD. Technically, angle ABD in this diagram has a second angle that also forms a linear pair with it. It would be this angle here, angle CBA or ABC. If you take a look at these two angles together, do they have a common side? Yes, they are adjacent. And look at their non-common rays. Oh, look, they form a line. So we have another pair of we have another linear pair in our diagram, and there are two others that I'm not going to show you. But when we have two lines crossing, yes, there are three total linear pair or four total linear pairs in this diagram that we can investigate. So be on the lookout for linear pairs and vertical angles. You'll see that we already used that definition of adjacent in the definition of linear pair. So just keep that in mind, right? Linear pairs have two things, adjacent and their non-common sides form a line. Complementary angles. You guys have probably encountered complementary angles in the past. Complementary are precisely two angles whose measures sum up to precisely 90 degrees. Meaning that if I had two angles and I add them together, find their sum, right? Every angle has a measure. If the angle has a measure, I can add those measures together, and if they equal 90, then great, I've got myself complementary angles. This doesn't mean that the two angles have to be adjacent. They could be any two angles, adjacent or non-adjacent, and I can get complementary angles out of them. For example, in the diagrams below, the first example are two adjacent angles. We have this one here and this one here, both adjacent because they have this common ray, and their sum forms a right angle, or 90 degrees, which means they have they're complementary here. Over here, we have two separate or non-adjacent angles, but look at their sum. 60 plus 30, that's going to be 90. We have our pair of complementary. So just because you hear complementary, it doesn't mean they have to be adjacent. They could be separate. That just means their measures add the 90. With complementary comes supplementary. Supplementary angles have a very similar definition. We're talking about, again, two angles that sum to precisely 180 degrees. So I add these two angles together, I get 180 degrees. Once again, they might be adjacent. It's not guaranteed. We don't have to say that they are because they're supplementary. Here we have, in the first example, these non-adjacent angles. Look at their sum, right? 60 and 120. That makes 180. Great. Those are supplementary. But we have another example here. This example looks actually kind of familiar, doesn't it? The second example here, it shows, oh, look, the two adjacent angles sum to 180. But there's something else going on here. I wonder what it is. It's a little bit of foreshadowing for us in the next chapter. There's some relationship in this diagram that relates something we've just talked about to this new definition of supplementary. So we'll talk more about that in the future. Let's move on. Let's talk about a right angle. A right angle is an angle whose measure is exactly 90 degrees. All right. When we want to give the reader or give the viewer of our diagrams here the information that we know an angle is right, we put this little square in the vertex of our angle. So there's this little square down here in the angle that denotes that's a right angle. Okay. If I were to try to draw a right angle on the board, just say, hey, here's a right angle. If I were to say, hey, look at that angle, what would you say? Is it right? We don't know. It appears to be right, but we can't go off of what it looks like. We really need that little right angle marker, little square in the corner to say, ah, yes, that is a right angle. I like to joke around with some kids and like I'll do this. I'll say, hey, look at that angle there. Now let's make it a right angle. And they're like, what? Oh, you can't do that. It doesn't. Oh, it bothers me. It's all right, right? That's still a right angle. Okay, even though it doesn't look that way, may bother you, but that right there is a right angle because we indicated it, we stated it with that little square in the corner. All right, let's move on. Let's talk about perpendicular lines. When two lines intersect such that they form a right angle, we call those lines perpendicular. Note that in the definition, I didn't say it forms four right angles. And even in the diagram, I've only denoted an angle, one of the angles, with the right angle square. I did not denote them in the other three. I wonder why he didn't put those right angle markers in there. We're going to talk about that in the future. When it comes along with the definition, We simply say that when two lines form a right angle, a meaning single right angle, we can call them perpendicular. All right. We'll talk more about why we didn't say four right angles in the future. All right, we'll talk more about that. But for the definition, keyword there, definition, a right angle forms one right angle when we call them perpendicular. All right. Let's talk about a straight angle. A straight angle is one whose two sides form a line, meaning their two rays form a line. We call that then a straight angle. Down below here, angle ABC is a straight angle. Now you're wondering, wait a minute, 90 degrees, right? A right angle, we said measures 90 degrees. The straight angle, where's its degree measure? Why didn't we say in the definition it measures 180? We're going to talk about that in the future. Okay. For right now, though, the definition and only the definition of straight angle simply says it's an angle whose two sides form a line. That's it. So we're not going to add or take anything away from the definition. So we're gonna come back to straight angles in the future. We'll talk more about where do we get that measure from? Where do we see that 180 degrees? But for right now, simply the definition: two sides form a line. We also have the acute and obtuse angle. You guys have seen these before. Acute angles are very simple to define. It's just simply that an angle whose measure is less than a right angle. So if we've got a right angle and we have an angle that cuts into that right angle, then we know that it must be acute. It's smaller than that right angle. An obtuse angle is one in which the measure of the angle is greater than a right angle, but less than the measure then of a straight angle. So if we have a right angle and we cut a little bit further out of that right angle, then we've got ourselves an obtuse angle. We're going to look at an example here of actually an illustration of a right angle, an acute angle, obtuse angle, and even I think I will talk about straight angles in the future, but we'll see an example of the right obtuse and acute all within the same diagram. So here's a quick illustration of showing how can I know for certain that an angle is acute, and how do I know for certain that an angle is obtuse. So if we take a look at our diagram here, we're given angle ABQ as a right angle. If you note that we've got that right angle marker in our diagram. What can I say about angle ABP? Well, angle ABP, this ray cuts right into that right angle, which means it has to be acute. So ABP must be an acute angle. Could I say the same thing about angle PBQ? Yes, angle PBQ is also an acute angle because it cuts into that right angle. It's smaller than that of that right angle, which means it must be acute. We have an obtuse angle in our midst. It's already kind of given in here. It's this one that rotates all the way over here. That is our obtuse angle. ABC is obtuse. I know it's obtuse because now it's greater than that of a right angle. If I were to extend this ray out here, notice then that it's also less than that of a straight angle, meaning I have an obtuse angle. But there is a question I have for you guys here. What can you tell me then about this angle here from ray BP to this ray BC, this angle that I've marked here? What is that angle? Is it acute? Is it right? Is it obtuse? A lot of students are going to say it's obtuse, and I'll ask you why. And they'll say, it looks like it. We can't say that that's obtuse based on what it looks like. Okay, looking like something is not a true justification. All right. So this angle PBC, this would be an example of where we use the letters CBD, cannot be determined. Okay, we don't know. We don't know if it is acute. We don't know if it's obtuse. We don't know if it's right, but we do know it has to be one of those. It's just with the information given, I don't know. So CBD cannot be determined. All right. So keep that in mind. We'll see this cannot be determined phrase used quite often in our year here of geometry. Let's move on then to our very last definition, reflex angles. We're not going to talk a lot about reflex angles, but I do want to mention them because it turns out that they do sometimes show up on the PSAT or SAT tests you will take in the future. So a reflex angle is an angle whose measure is then greater than that of a straight angle, which means if we rotate from one ray all the way over to the straight angle ray, but we go a bit further, we've then produced ourselves a reflex angle. Reflex angles go then from greater than the measure of a straight before we get all the way back around, right, to this angle here. So that entire area of rotation is where we'll find our reflex angle. So this angle, angle CBD, is in fact, and don't be confused that CBD is actually referring to the letters, cannot be determined. This angle CBD is what we call a reflex. It goes to the straight and then slightly past that angle, turning it into a reflex. You'll see that we will not talk much more about reflexes, but just in case you want to know what is that if we go past the straight angle, it's a reflex angle. With that, that is the end of our lesson 1.4. Make sure you're working on then the 1.4 worksheet. If you do have any questions, please do not hesitate to ask me. And that is our end of our lesson today. So be good and do good.